And the main reason for doing that was at that time, NASA and Lockheed Martin were really busy working on the X-56 program and the body freedom flutter program. So, for example, Pete was working on the PAA, Performance Adaptive Aeroelastic Wing program. And we were thinking that, like, okay, in Europe, we should also build an expertise to work with flutter technology. So flutter technology becomes very important when you have aircraft with higher aspect ratio wings, as you want to have more and more aerodynamically efficient aircraft with higher wingspan. All the flexible problems are becoming more and more pronounced. And so we actually developed a demonstrator based on the wishes and the inputs of our industry partners, mostly Airbus. They wanted to have a demonstrator which resembles a conventional configuration aircraft, not a body freedom flutter aircraft, what the X-56 was. And in this project, we built up our tool chain to be able to model such an aircraft, not just only this particular aircraft, but go from modeling to automatic control design. And we started also flight testing. Unfortunately, in this first project, we were overambitious, so we didn't go all the way till the end to test our ultimate objective, but we had some very interesting and important flight tests. And yeah, what was also very important is really bring together industry and academia in Europe to work on aeroelasticity and flight testing things. So just a little background on our aircraft. So we on purposely put lots of sensors on the aircraft. So what you see here is that, like, in the wing, you have multiple inertial measurement units measuring both the acceleration and the angular rates inside the wing. So to be able to reconstruct the flexible behavior of the wing, we have lots and lots of actuators to be able to control the motion of the wing. And we developed our own flight control architecture to be able to react very fast, because we would know that flutter is a kind of a very fast dynamic phenomena. So you would not be able to allow, let's say, space to kind of have more and more delay in your loop and more, let's say, reaction time. And coupled with that, we also developed the hardware in the loop infrastructure, which came very handy during the time of COVID, that we could test algorithms and flight control computer parts in our lab instead of going to Munich, where the aircraft was sitting. So we were very lucky that we had a follow-up project from 2019, which was also led by me, and mostly the proposal was also done by me. The basic idea was that, okay, like, we know flutter is a limiting phenomena if you have an aircraft, but what happens if you put controls into your multidisciplinary design optimization and you kind of open up some design freedom in your aircraft optimization space that you can account for active control technology, and you can, for example, delay flutter by a control law, which can lead to, let's say, 7 or 8% reduction in fuel consumption according to our initial calculations. So what we were saying in this follow-up project, that, okay, let's carry over the demonstrator, and we wanted to validate both the control technologies and the aeroservoelastic modeling framework. And what we said, okay, let's better understand how control and aircraft design couples. So what are the main challenges if you have a flexible aircraft? You have multiple phenomena happening at different frequencies. So first you have the zero frequency, the trim. You have to optimize for trim to be able to get the best fuel consumption. Then you have the baseline flight control laws, which are kind of low frequency. Then you have different dynamic loads by gust and by turbulence. And then the highest frequency phenomena is flutter. So we have to do nested feedback loops. They would interact with each other. And you really have to develop kind of a systematic framework, because if you design one feedback loop without taking care of the other, then you would have some troubles. And so we had lots and lots of things in the project, but I'm going to focus on the flutter control part, because that's the highest frequency, the most challenging thing. What we were doing in the flutter control problem, we initially decided that, like, okay, we will have two kind of competing designs, one of them by DLR, the other one by Sztaki. Both of them would be kind of based on the high fidelity model developed by DLR. And then one approach, which was done by DLR, is a so-called H2 optimal blending. So you would take all your sensors and you would try to blend the sensors in a way that they are sensitive to the flutter mode. So you generate one single output, which is kind of representative of your mode, what you want to control and what is unstable in our setting. And then you would just design a very simple dynamic controller. So the in this blending is actually a static thing. And the Sztaki approach, what we actually developed together with Pete, was based on kind of a structured controller synthesis, which was kind of the need of industry, that they don't want to have a very large, very complex control kind of gain or very complex dynamics. So we said, okay, let's restrict ourselves to have a very simple dynamics, but we want to do an age infinity optimization to be able to optimal for, let's say, disturbance rejection or sensitivity. And so first thing what you have to deal with these aeroservoelastic problems is you have a model coming from, let's say, another partner, DLR, where you have very, very high state order and no control design method, or not no, but like all the control design methods would have very hard time working on them. So we developed first a model reduction technique or framework, in which one of the most important thing was we wanted to retain the physical insight of our system. So we developed the model reduction technique where you still retain the physical meaning of the states. And that can be done by a subsystem approach. So we individually reduce the aerodynamics and the structural dynamics, and then put them together afterwards to kind of assemble a model which you can still analyze certain engineering phenomena. And after that, like, this physical approach also allows you to introduce uncertainties in your plan. So what we said, we just don't want to have a design for let's say, a nominal plant, but what we wanted to have is to represent physical uncertainties both in the modal frequencies and modal dampings of our aircraft dynamics. So what you see here is, with the subsystem approach, after reduction, we were able to introduce parametric uncertainty in the model. And of course, since we wanted to have a simple control design, we then decoupled the lateral and longitudinal dynamics to be able to have like two flutter modes. One is symmetric flutter, the other one is asymmetric flutter. And then we went to design a controller. So it was kind of natural from the beginning that we would use the outermost ailerons. So there was no question that, like, the wingtip actuators would have the highest control authority on the wing bending and torsion motion. But we have to kind of come up with the best sensor selection. So as I said, DLR was doing a full all sensor blending. We wanted to do something which is more explainable. So we said, okay, let's pick certain sensors and then blend them manually and do a similar control design, like a SISO control design. But let's put some engineering thoughts that, like, okay, what is the best way of picking these sensors? So normally, what is the state of practice in aircraft industry for measuring vibration is to use accelerometers. And what is actually interesting, that like accelerometers would be picking up wing bending motion, but our flutter is mostly torsion dominated. So we went with an unconventional selection that we wanted to have the torsional rate sensors in our control loop, and we did for the symmetric motion, we selected, kind of blended the left and the right, and subtracted the center body motion, and for the asymmetric, we just had the difference of the two. But just to make sure that, like, during flight test, we have a backup solution which is maybe more robust, we also did a control design where we used additional sensors, not just the torsion, but the bending rate. But that was kind of just only for our own sake, to make sure that if something doesn't work in flight test, we would have a fallback option. So then, if you massage your system like I explained to you, then you would end up with a design model, which is in this case a SISO model. But you can see that there are some pretty nasty, unstable behavior at the flutter frequency, and there's lots of variation of the plant as you change speed from let's say below flutter speed to over flutter speed. And it was even, we didn't prove it, but it was even kind of obvious that PID controller would not be able to stabilize these planes. So these are such complex dynamics that simple controllers would not be able to stability. And of course, we still had the uncertainty in these plans, so that we wanted to design a controller which is robust for a parameter variation of damping and also for a range of velocities. So, as I said, we picked our favorite control design methodology, H2020, but not like a full H2020 solution. But what we said, for the symmetric modes, we have a 4-states controller, and for the asymmetric, we have just 2-states controller. That was kind of an iterative process to come up with these states numbers, but the lowest possible with which we can have meaningful results. And the control setup, like the weighted interconnection, looked like this. So we had just only sensitivity minimization, and we penalize only the actuator input. And we also had like a prescribed filter to match the bandwidth of the actuator. So this is your only free parameter, and you prescribe the structure, and of course you have a delay in your loop. And what we wanted to have is to have a controller which stabilizes a range of velocities with one single controller. So, of course, if you have a stable system, you could have performance, and it's kind of the easiest problem to have. You can have robustness as well. You have certain frequency range when you have degradation, and then high frequencies you usually have no control action. Of course, if you have an unstable system, then you have even more difficulties. And if you have right half plane zeros as well, then you might not be able to do anything with performance. You just want to have stability. So we set up our problem as a sensitivity minimization, that we didn't want to achieve any kind of performance, just to make sure that the plant is stable, because in certain combinations, we had also right half plane zeros in our design plan. It was kind of a long process to have the best kind of trade-off between sensor selection and achievable performance. But for example, the accelerometers would not give you good results because they had like a direct feed through, and that would lead to further complications in the control design. So then we had the plant from DLR, we reduced it, we designed a controller for it, and then we started analyzing first of course, in simulation. So how the whole trajectories look like. This is like what you see are the two flutter modes, which are becoming unstable around 50 meters per second. And then, of course, because you might also have some unstable rigid body dynamics, like slightly unstable spiral mode, first you have to close the baseline controller to stabilize your aircraft in a rigid body flight. So we analyzed, and the flutter modes did not really change by the baseline controller. We were kind of designing the baseline not to interact with these high frequency modes. So that's good. And then we applied the flutter controller, and what you see is that those previously unstable modes are delayed significantly. But of course, that's also like a question that like usually you want to design the fast feedback loop first and then the slower feedback loop. So in our case, it was also a kind of a trade-off that like, okay, do you want to design the baseline controller or the flutter controller first? But we ended up kind of designing them separately and then looking at them putting together. So the final evaluation or analysis was that what are the margins of these controllers? So as I said, we had different designs, like taking into account like a velocity range. So you have multiple plants in a range of velocities, and you designed one single LTI controller to design that family of plants. And then we analyzed what are the disk margins, like the gain and phase margins of these controllers. And what we found out that the 4-input and the 6-input controllers did not really have significant like differences in terms of margins. But of course, if you design your controller for a larger range of velocities, then you lose robustness even in the low velocity domain. So what we ended up flying is the more robust version, because we wanted to make sure that we will not crash. So this is kind of the setup. We built all our control design and analysis framework. And parallel with that, we started flight testing our aircraft. So there were some logistical complications that, for example, the EASA rules in Europe changed, where you can fly such a large 7-meter wingspan, 65-kilogram aircraft. So we moved from DLR Munich to DLR Cochstedt, which is in the middle of nowhere, where you cannot hit anyone if you have a problem. And of course, we started checking in 2022 the baseline controller. We started injecting maneuvers so that like you would do the rigid body and also the flexible identification of your plant, and started preparing for flutter control. And of course, we have a fully instrumented aircraft, so it's generating lots and lots of data. You have many opportunities to work with that data. It was kind of funny to also develop all the kind of post-processing tools to be able to very quickly assess the flight and say that like, okay, is it safe to get the next flight test data point or not? What was also a very big complication during the project is we realized that this flutter frequency, which is almost 9 hertz, this is something no off-the-shelf actuators are able to handle. So we developed actually our own actuator to be able to control the outermost flap. And you could see that this is not your average servo actuator which sticks into your wing, but it's kind of bulky, big, and heavy. And because of that, we actually ran a parameter sweep that like what is the best position to put this actuator on the wing. What you see here is that like in these different locations, the flutter frequency changes from 8 to 5 hertz. Like if you have the wingtip mounted actuator, then you have low frequency. And here you have very high frequency. And also the flutter speed changes from 48 to 76. So our aim was to have the lowest possible flutter speed, but also the lowest possible frequency, because then you would not be required to develop such a crazy actuator. So by crazy actuator, I mean, you could see it on the wing, and you could see in a static test stand that if you start actuating just the actuator, it actually starts shaking the wing itself. What you also see here is we put in a safety mechanism. So this is a rod, we call it a flutter tuning rod, in which you have a little mass. And it's a safety feature that if you release it, a mass goes next to the wing, and then the flutter speed is increased significantly. So it's a safety net that if we trigger it, then we have very different torsional dynamics over wing. But yeah, you see there's quite a big motion just only by actuating the direct drive. So as I said, in 2022, we started to fly the aircraft. We developed this ground control infrastructure, and we were also trying to model the flow around the aircraft, how good the predictions or how good or low fidelity CFD tools are, and we were also doing some oil film visualization if we have flow separation or something like that. Also, in parallel with that, we developed kind of the monitoring framework and the flight test infrastructure to be able to inject certain maneuvers and in real time evaluate the results. And with all that data, we started updating our models. So lift, flap, drag models. And as I said, we were working first on the baseline controller, which is very important for flutter because you don't want to overshoot your speed, because then just by accident you could end up in a dangerous zone. And yeah, we have pretty good results even initially on the rigid body motion. What was very difficult is to be able to control the velocity, especially because we have a jet engine which has a very large lag and not too good kind of interface with it. So we ended up designing many different approaches and testing them. So you see 3 different control designs for the velocity tracking, and we were evaluating them and kind of comparing them, which one would be working the best. And in parallel with that, as I said, we were not just only using the data after we finished the flight, but we were also running so-called operational model analysis. So we have all these sensors inside the wing, and with those sensors, we were able to characterize the modal properties of our aircraft. And it's actually something which is done in large aircraft, but we were able to squeeze it down to a Raspberry Pi, which was a big feature on its own. So what you see here is during the flight, we are able to track the different modes. So it's kind of online system identification. We are able to track the frequencies and also the damping of these modes. And of course, if you are getting closer to flutter, then you would see certain frequencies changing and the damping rapidly dropping. So it was kind of a safety feature that we conduct one flight, and if we can still have flight time to go to the next text point, we would take a look at these data and see that, like, okay, do we have the confidence or not? So what comes out of these are these mode shapes and their corresponding frequencies. Yeah, and of course, as I said, we were doing kind of system identification to get better models based on which we can synthesize better controllers. So, and that we were very happy with all the progress, but then in 30th of August 2022, we had a flight test which did not go as well as planned, and I still have goosebumps now. If I think about this, you will see what I mean. So we have a little bit of a mishap, I would call it, and you see the aircraft is doing its normal maneuvers, and suddenly just the parachute opening up. It's a safety parachute. So what actually happened is both telemetry or both RC links were cut because of some certain geometry, and yeah, this is the bad part. that we ended up having like losing our demonstrator aircraft, what we built since 2015. So big questions were that, like, okay, why the connection to the aircraft was lost, and next thing which caused the fire, why the hell the engine start again? So it was discovered that it's very bad, like if the antenna points really towards the pilots, because that's the blind spot of the antenna characteristics. And we went back and analyzed that, like, okay, how shall we redesign the RC system to avoid this in the future? But the bigger problem was that when we did the safety analysis of our aircraft, we were saying that, like, okay, parachute open, so end of the investigation. So we were like, okay, if the parachute is open, we cannot do anything. But it turned out that we forget about the fact that when it was hanging on the parachute, the reception to the RC system actually reconnected. And because the RC system was still in engine on mode, it actually restarted the engine. So the lesson is that never stop your safety investigation when the aircraft is still in the air. So yeah, but we were very, very eager to still conduct flight tests. So this happened on the 30th of August 2022, and the project finish date was June 2023. So we made the decision that we will rebuild the aircraft, and we put together a very ambitious test campaign to still conduct the flight tests. And of course, we have to abandon certain goals of the original projects. But yeah, in 2022, we conducted 14 flight tests, collected lots of interesting data, improved our modeling or control framework, and learned lessons the hard way. So my colleague from TU Munich called 2023 the rush for success. And what we did, we actually rebuilt the demonstrator. So the original build was a little haystack. We now have the opportunity to rebuild it in a much better arrangement. And in April, we went out and conducted the ground vibration test of the aircraft. So crash was end of August, and in 7 months, we rebuilt the aircraft, and we went to start conducting the vibration test. with this vibration test, we confirmed the models and updated them slightly. We have an updated flutter speed of 56 meters per second, and we also analyze the behavior of these flutter stoppers, so it can significantly change the behavior of the torsional mode. So it's actually effective in let's say, delaying flutter. What was also important is we were testing an active control system in a ground vibration test environment. So we learned a lot of the problems that if the system is not passive, but you have active control surfaces and control laws, then GVT is not that easy anymore. And yeah, as I said, in April, we conducted the first flight test of the rebuilt demonstrator. So we were quite happy with how it flew, and relieved a little bit that maybe we can save the project. So, but all the interesting things were just to come. So yeah, maybe this is just a ceremony to sign the aircraft after the maiden flight. And we have two concentrated flight test sessions. Like all the team members were in Cochstedt, everyone working around the clock to be able to get as much flight as possible. So everything was actually ready after a few flights to be able to go up to the flutter speed. So as I said, the velocity tracking was one of the most important. So what we were doing is we were below flutter speed, which is the safe region. We were doing like switching on and switching off the control laws to be able to compare the without and with control behavior of the aircraft, to make sure that we are actually at the same day with same flight conditions, comparing two things, and not different flights with different configuration. So what you see here is this part is when the controller is not active, and that part when the controller is active. This is the flap deflection, this is the wingtip gyroscope, and this is the wingtip accelerometer. And if you look at the time domain data, this is an early flight below flutter speed. You would not be able to say anything. Is it working or not? Definitely, there's different spectral characteristics, but who knows which is better or not. So when you go into the frequency domain and analyze the frequency content, then what you see is that without the control law, you definitely see a sharp peak, which is kind of resonance. And with the control law, these resonances are significantly damped. So we were kind of confident that, like, okay, with all these sensors, with the DLR controller, which takes credit of all the wing IMUs, we were still able to do something which is meaningful, let's say. And what you see in this chart is also similar. So the open loop with a large peak with the left and the right wing, and then the closed loop. Both on the accelerometers and the gyroscopes, you see damping of these modes. The other controller which flew, which is flight 34, that's the Sztaki controller. Here you can also see the accelerometer response in frequency and the gyroscope response in frequency. Well, just remember that this controller only uses the gyroscopes, but still in the accelerometers, you can see this very, very big damping of that resonance mode of the flutter mode. So it was kind of reassuring for us that everything is working as expected. What was also very nice as an independent assessment of our control laws and tools is the operational model analysis, which is purely data driven, not model based, was also doing an analysis of the modes and the frequencies. And what we have seen is the two modes which are participating in the flutter. We see a trend that they would kind of like go near each other, and we would see the damping trend of the torsional mode going down towards zero, which would indicate that we are going to have flutter. What was actually very funny when we were analyzing this plot is that the theoretical group from DLR actually had a kind of a Heureka moment, that the 2019 paper was predicting exactly that as you start going up, like one of the mode like gets the damping lower and lower, and the other mode get more stiffer and stiffer, and then you would lose the possibility to identify and track that mode. So this was exactly what they were predicting in their simulation-based paper. So we said, okay, let's go beyond flutter speed, because it looked like the controller is working. So what you see here is flight 36. You see the aircraft flying in large circles with constant velocity. This is the velocity profile of the flight, and what you see is there's nothing happening, which is good. Then we turned the controller off, and you could see this sudden vibration, which is kind of close to flutter, and then we actually turned the flutter stopper on, so then the vibration kind of fade away. But we were kind of happy with the flight and the results, but there's always a little kind of the little devil in your shoulder that like, oh, was that really flutter? So we said that, like, okay, we conducted all the flight tests what we wanted to do, so then let's have one last flight to go all out. And that's flight 37 is gonna be. So what you see, oh, okay, sorry. First just the analysis of the results. So we conducted flights at 59 and 57 meters per second. Both of them are beyond the open loop flutter speed. And you see that these resonance peaks, which were visible in the open loop, are not that pronounced in the closed loop. On the gyroscope, you start seeing some of these resonances, but they are not that sharp, and they are still clearly stable. But what is a side effect? So there's never a free lunch. You start seeing things in the higher frequency region. And this is something which we are still analyzing, because the ground vibration test went all the way up to 50 hertz. But here we are seeing things at around 60 hertz, which is beyond the GVT frequency. So we don't know yet why those things are happening. Yeah, it's just the explanation of that we have a very sharp roll-off of our controller. So the controller should not be acting in this frequency range, but still we see actuator commands in that region. So it means that probably the plant has some high gain, that in the feedback loop we still see activity in that region. But we also confirmed that if we turn off the controller, then we see this sudden kind of increase in amplitude, which is kind of saying that in open loop we were beyond the flutter speed. And what you see here also is when we release this flutter stopper, suddenly the vibrations were shrinking, and we were no longer in a slowly growing part of the gyroscope data. So, and then maybe I spoiled it already, but then we said, okay, let's confirm that what we have seen is really flutter. So what you see here is we are accelerating with our aircraft, and as I said, the predicted flutter speed was 56 meters per second. So as we are approaching that speed, you could see that, like, okay, this is something what you don't want to see on an airplane where you are sitting, that the wingtip is just doing crazy things like that, and even more. Just bear with me for a moment. So at this time, we were 1,000 meters away from the aircraft in our ground control station, and you could see that this is something what is not really good, and but nothing crazy with the aircraft itself up until this point. It's like, but from a ground control station, we were still not able to see that, like, okay, something actually broke off of the aircraft. So we were still accelerating, and we were very, very sad that, like, we were like looking at the NASA and Lockheed Martin kind of experiments where the aircraft disintegrated. Aircraft was still flying, and we were like, oh shit, like the whole project was for nothing. And yeah, as we accelerated even more, even the other rod started to break off, and then, like, with the binocular, I was actually see that, like, oh, there's something hanging on the wingtip of the aircraft. So then I was like, okay, guys, maybe we have achieved what we wanted. So we were relieved, and we were very happy that we actually showed that we have flutter, and we also showed that with the active controller, we were able to dampen the oscillations and stabilize the plant. So in 2023, we performed, after this terrible accident, 14 flights with 380 minutes of data, did the ground vibration test. We did all the analysis of the predictions versus the flight test, and they were matching quite well. And we were able to flight test 2 different controllers, and both the DLR controller and the Sztaki controller worked quite well. Of course, there are still these unexplained behavior. And even more interestingly, it's really a control structure coupling, in a sense that these 2 modes in the DLR controller were apart, and in the Sztaki controller, they were at the same frequency. So probably the structure of the controller and the feedback loops were different in the 2. That left and the right wing has different frequencies with one of them, and similar frequencies with the other one. So what we did in the project, at the end of the day, we developed avionics, both actuator sensors for flutter control. We validated a lot of the tools to be able to model, control, and analyze aeroservoelastic phenomena. We gathered 600 minutes of flight test data. We successfully demonstrated active flutter suppression in a conventional configuration aircraft in real-life conditions. And on the top of that, we were also feeding all that information back to how we should do aircraft conceptual design with controllers in mind. And what I just want to highlight is that all the flight test data what we collected is available online, open source. And yeah, there's a lot of opportunities, I think, to look at that data and do system identification or analysis. And yeah, I'm very happy that I'm here and I'm able to report about all this success. So thank you very much.
A few minutes for questions. Yeah. Well, thank you, Bill. Really nice presentation. I'll make sure my students who I'm going to yell at who's the center is the great. I don't, but when I look at your demonstrator aircraft, one of the things I kind of noticed was, in addition to having a high aspect ratio that induced the flutter, it appears to have some design considerations that make it kind of tough to intuitively look kind of tough to fly. It's got a V-tail. It looks like a little bit of anhedral to it. Was there?
So V-tail is because we have a jet engine.
Okay.
So you don't want anything. You don't want anything in the jet's flow.
Fair
and the dihedral.
It looks like it's a little anhedral too. But I don't.
Yeah, like I mean, it has to have this top wing configuration because you want to hang your actuator, and you still need a ground clearance. So yeah, like it was kind of a long process to get kind of some compromise between the Airbus guys and the TU Munich guys, and so I would not say anything that like, okay, it's good or not, or why we.
I used the adjective interesting.
Okay. So yeah, the main design constraint for 7-meter wingspan was that there's the largest kind of let's say trailer what the TU Munich team could have to be able to transport it on public roads. So there's a lot of constraints if you want to fly test aircraft.
Sure. You know, one of the other things I was wondering about in terms of just big picture analysis is ultimately your goal in active flutter control to you mentioned fuel consumption early on in the presentation. Is that the chief goal, or is it flight envelope enlargement that's really
the two are kind of related. So yeah, yesterday we were just talking with the guys that like if you want to shrink the margin, like which is in the certification requirements, to not to have 15% margin from the maximum dive speed to flutter speed. If you want to shrink that, then that's essentially kind of enlarging your flight envelope where you are safe to fly. So what you want to do is really let's say push your constraints that like you still want to make sure that 1.15 of your maximum dive speed is flutter free, but maybe you can take credit for an active control system between maximum dive speed and 1.15 dive speed. So what we were considering and what was also Airbus's, but I'm not speaking on behalf of them, what was their idea also that like you don't want to have this flutter control system as fully 10 to the power of -9 safety critical. You might want to do it as a 10 to the -7, so not as critical component. And then you say that like, okay, but by the way, this system works, but we are never going to be in that envelope where you have to take full credit during a full flight for this. Did I answer your question?
Yeah. No, that makes sense. I could ask a bunch more stuff, but
That's something more practical. Do you only have data, or do you have any of the simulators, or?
Yeah, we have the simulator as well. So we have mathematical models, like both reduced and I think the full nonlinear model with the large number of states. So little
the open source data that you put, maybe you posted models with the data or only the flight data?
So at the end of the FlexOp project, we posted the models as well. Right now, since we are still working a little bit on the data, we haven't posted the new shiny updated simulation model because I'm still trying to convince the DLR colleagues, if they are listening, convince them to still make some updates to the model. So there's the conference this summer in The Hague, like the FliPASED, for which we are preparing some papers. So it's work in progress, but yeah, we would be happy to share the models.
Can I ask one quick question following that? You mentioned taking the flight data and updating the models. I'm trying to understand what would you do to update the models? You have these like finite element models for the structure, you have panel codes for the aerodynamics, like, not like you're just updating a mass or like a 1 or 2 coefficients. How are you using the data to update the models?
So that's the DLR team, and so they have these tuning beams in the Nastran model, and they were fine-tuning the Nastran model to match the response better.
Okay.
So it's not so you have some degrees of freedom in your Nastran model, which were dialed in specifically to be able to adjust it after experiments,
Okay.
both the ground vibration test and also the flight test.
Thank you.
And yeah. Well,
Just out of my curiosity, how many people work in this project?
so I can tell you the budget. So actually, so like it's like there was 2 subsequent projects. In the first one, we had a consortium of 10 companies, and it was a 6.7 million euro project. And in the second one, it was a 3.7 million euro project with four partners. At any given time, I would say 30 to 40 people, not full time, of course, but associated with the project. Yeah.
I had a question. You mentioned like the -7 and the -9. What does usually go into the certification of your controllers? Like,
Excuse me, negative.
the -7, I think that's probability of failure.
Yeah, 10 to, oh, sorry.
10 to -.
Excuse me, what was the question?
What goes into the certification of your controllers? Like, if you have your controller and there's the aviation department, what do they require from you to say, okay, I can fly this on airplanes?
So usually it's actually a very good question to Pete, but what happens is usually like you have a simulator and then you kind of grid your entire flight domain, like different mass cases, different CG cases, and you have to show that for each given point in your flight envelope, you still have given margins like let's say phase and gain margins of your control loop. Besides that, you also have to show that the model what you use for certification is actually a good model, because if you have a non-representative model, then you are not going to be able to use that credit for certification. So usually they are updating the model in the early flight tests, and they are kind of like opening up the flight domain with subsequent flights to kind of say that like, okay, I said the model looks like this, and in flight tests you validate that really your model is close to that, and then you do the analysis in a say both in time domain and also in frequency domain.
Yeah, that's my question. Like, how do you say, like, how do you define close enough? Like, how close is close enough? Or
So the 10 to the -7, it has nothing to do with the control law itself. It has to do with the components which are inside the control system. So you have a flight control computer, you have sensors, you have actuators, you have a mean time between failure of your controller, you have the mean time between failure of your sensors, you have a data bus and redundancy of your sensors. And then you do a fault tree analysis, and then you say, okay, like what is the cumulative failure rate? And then, but that's somehow decoupled from the method what you use for control design. So
It's 4:30, so maybe we should thank the speaker again, and Bálint will hang around if there's other questions.
thank you very much.
So one other thing I was thinking, so there is a human.
Hi.
Oh, Chris Vermillion, by the way.
Great talk. I like.
Thank you very much.
Main stuff, you know?
I like to see field testing results. I have respect in the world for people who On the ground, two pilots. Now, were they just commanding waypoints or were they commanding anchor points or what?
So what we did, so initially we wanted to fly like pattern and just accelerate, stay the flutter domain and then decelerate. It's, because of this operational model analysis, you need at least a 30-second window to reach to be able to capture the modal data. So what we ended up doing is we have a 900-meter radius circle, and the controller was actually commanding constant velocity, constant altitude, and constant bank angle.
Okay.
So constant bank angle because
Yeah, I did notice the ailerons were not.
Only thing is that like we didn't want it like if there's a wind, we didn't want to kind of have a circle, but we wanted maybe it's like a helical pattern if there's a little wind. So what we do is takeoff and landing fully manual. And then when we are up in a good location where we could start, then we engage the autopilot, which was doing this. And if there was strong wind, then we had to correct, maybe after 2 circles, we had to bring the aircraft back by the manual pilot to start again from a good location. So it was like we had a tower and pretty strict rules of like what can be done. So actually in this dangerous flight test, we have to send people to different roads to say that like, okay, there is danger, and especially after we crashed, they were more.
Yeah, I did. Yeah, I worked with tethered system kites, and so you know, our systems are at least they're on a tether until they break loose from the tether. But and so there's a little bit more of a constraint in terms of how many bad things can happen.
And you work with like rigid tethers or like a parafoil?
Oh, you mean the foil? So the kite, all of the kite systems that I've worked with have been rigid kites.
No, it's just
you're familiar with it.
Yeah. I know a few guys at ETH who were doing this. Black thing.
Yeah. So I'm the other area of focus actually. I work with underwater kites as well. So of course those are rigid. Actually, in the US, there's just so much more of an appetite amongst the water power people who are kind of out there ideas. That means the actual controller doesn't like look at the show like that. The tough thing with kite is you're controlling the kite with tethers rather than with onboard control circuits. So in addition to there being significant lag, the control authority
because of the flexibility of the tether. Okay.
Yeah. I mean, you get a response immediately when you winch in, but the ground is not exactly the same as what's happening in there because you're pulling the catenary out of the tether. But the other thing is 2 tethers don't function quite the same as ailerons do, and over the past century, how fixed-wing aircraft fly, and a similar statement cannot be made for fabric. I think some of these guys probably yeah, really interesting.
Thank you very much.
I guess my other thing, my other technical question was these are going like 60 meters per second or somewhere. Yeah. We had a flutter speed of 56. Yeah. Because you're because of air.
No, very first design review meeting, guys from Airbus said that like, okay, if it's a blended wing body, then they are leaving the project, nothing less. They are leaving the project. And the other requirement, it has to have at least 20 degrees sweep back to look like as a future generation Airbus aircraft. So yeah, like, so and that's a very good question actually, because like as you have less sweep back, you are more pronounced to flutter, so you have earlier flutter, and you have less easier to control. That's life. Not a
Just the component.
you must made it more difficult just for fun.
That's flutter phones not still just like that part signal. Then you go to flight test, but flight test should be verifying everything. Their data is.
And also all my code and was realized like.
Just like, we do some flight test to verify all this.
Is that like without the
Pretty obsolete, so.
like
You
was
might
that
not
the
be
controller that you
able to
used
show what
throughout
the song
all
is.
the simulation in flight, or did you eventually?
I'm gonna. Let's see if I can get some.
Well, like half of the airplane is here, the other half is here because they cracked it with the big, like, hangar type, like, building. Great.
Here, Hungary and Lunera made one approach to handle uncertainties in the structures. It's developed another how to handle uncertainties in the structure design, and that was kind of
Now they're pushing for reducing these distance.
so we didn't want to, and telling you honestly, like this is not very large
Like a supervised
reflection, so
so like
we
if
don't
everything
have
fails,
that
this would
much
take
more in there.
But then I was thinking maybe
So
some
you kind of brought that into it.
and then you control it.
Okay.
Having developed systems.
I mean, so it's like a beam,
Some things are about.
like flexing around,
Some things are about, like,
so it becomes a very large reflection, and
take
you
over, well, it's
start seeing
sometimes,
these,
but it would be nice to have a
like
controller
the
that just takes over and like.
I think that like your wingspan is reduced as you have higher deflection, but it's just
But I think like they're saying
slight
thing here,
oscillation
that
around
expects
this
that things will
nominal
take, like,
weight, and linear approximation is pretty okay.
But you did the gain scheduling, correct? Did you use gain?
No, we didn't do the gains on the.
How they handle the speed
Speed
range?
controls, so the velocity and the rigid body controllers were gain scheduled, but the model controller was not. So what the chart what I showed that we designed one single controller which is robustly stabilizes a range from 48 till 62 meters per second. And that was one single